So welcome to Robotics 1. In today's class, we are going to talk about the robot when you have a slender rod. So the problem is something like this. If you recollect, earlier we looked at the problem where we had a pendulum where the mass was located at the end. So mass was a distance L from the hinge. And then if you remember, we derived the differential equation of motion theta double dot E by L theta is equal to 0, and we solved it. Now the question comes is, imagine instead of being a slender just a mass that is located at the end point, if there is a pendulum wherein that pendulum has a non-zero inertia, then what? So basically, this is called as the slender rod. Which means you have this rod of length L, and this mass M is distributed on the slender rod. So M is distributed. Now, whenever you have a problem like this, what I want you to understand is this problem can be solved multiple ways. Now, what I'm going to do is, I'm going to write this problem as something like, if you want to find out the kinetic energy of this rod is going to be kinetic energy of translation plus kinetic energy of rotation. Kinetic energy of translation is this mass M is located at the centroid. So this is going to be M multiplied by the velocity of this mass. Velocity of this mass is going to be L by 2 theta dot square by 2. So basically 1/2 m v square plus 1/2 I omega square, and this equation is going to be 1/2 m L by 2 theta dot square plus 1/2 I omega square. Now I is called as the mass moment of inertia. So mass moment of inertia is nothing but if you consider this slender rod, the masses are distributed along the length. So what we want to do is, we want to find out m r square, and you integrate this, and what you get is you get the mass moment of inertia. And the equation, so basically this is written something like this, r square dm. So, and then this goes from minus L by 2 to plus L by 2. So here minus L by 2 to plus L by 2. And then what you can do is, you can actually integrate this, and you will get the equation for mass moment of inertia, which is 1 by 12 m L square. So I, for this slender rod, is going to be m L square by 2. And please try to understand, this mass moment of inertia is about this point, centroid. If you were to find out the mass moment of inertia here, or if you were to find out the mass moment of inertia on the other side, depending upon where you take your moment, mass moment of inertia would be different. So once I substitute these values over here, it is going to become 1/2 m L by L square by 4 theta dot square plus 1 by 12. If you look at this 1 by 2, I is going to be 1 by 12 m L square, and omega is going to be theta dot square. So this is going to be the kinetic energy. If you look at this equation, if I write this equation down, this is going to become 1/2 m L square by 4 plus m L square by 12 theta dot square. So this equation becomes 1 by 12 m L square by 3 theta dot square. So this is the equation for the kinetic energy for the slender rod. Now, one thing I want you to understand, the potential energy equation, PE, is again, if this is your datum, this is going to be L by 2, this is going to be L by 2 cosine theta. So this is going to be m minus L by 2 cosine theta times mgh. So mgh, and you have to find out the Lagrangian. L is equal to T minus V, which is kinetic energy minus potential energy, and then you have to use the Lagrangian equation. So d by dt partial theta dot partial L or partial theta dot minus partial L by partial theta is equal to 0. And once you work this math out, you will realize the equation is going to become ml square by 3 theta double dot plus ml by 2 g sin theta is equal to 0. So this is the equation for the so ml square theta double dot mgl cosine theta. Yeah, so this is the equation that you get. Now, so please understand what happens is we are looking at the case when the mass is distributed. Imagine this is the link, and this link has this length L, and this is the height of the link, and then this is the width of the link. And what I'm going to do is I'm going to show the axes. So I'm going to call this Z axis. I'm going to call this X axis. I'm going to call this Y axis. Now, this three-dimensional object will have something called as Ixx, which is mass moment of inertia about X axis. It will have Iyy, which is mass moment of inertia about Y axis, and it will have Izz, which is mass moment of inertia about the Z axis. So it will have mass moment of inertia about X axis, mass moment of inertia about Y axis, and mass moment of inertia about Z axis. So if you look at the basic definition of mass moment of inertia is nothing but r square dm, wherein what we are interested in r is the distance of that mass from the centroid. So what that means is, if you have a mass over here, what I want to do is, I want to find out the radius at which this mass is, and then integrate it for all the teeny tiny masses that is on this rigid body. So think about that. You have this rigid body. This rigid body has these teeny tiny masses, and I am finding out the mass moment of inertia of this individual teeny tiny mass, and I'm integrating this over the entire body. So when I'm looking at Ixx, what I'm doing is, I need to perform the integration over z square. So integration z square plus y square dn. Because please understand, the radius, I'm going to take the moment about x. So all the radii that I have, those radii are about z and y. Can you see the z and y? So all the radii are about z and y. If I take the moment about z, all my radii are, or whatever radii they are resolved in x and y. If I take the moment about y, all the radii are resolved around x and z. So what that means is, mass moment of inertia about Ixx is z square plus y square. Mass moment of inertia about yy is z square plus x square dm. And mass moment of inertia about zz is x square plus y square dm. Now what that means is, if you perform the integration, understand, performing integration is very important, because the limits of this integral are dependent on where you are performing the integration. For example, as in the earlier example, if you are performing integration about this point, you would be doing integration from minus L to plus L minus h by 2 to plus h by 2. Everyone understood this? So your limits of integration, understand, you are varying. So if you are varying z and y, then you are performing the integration about in the z direction. So you have plus w minus w, y is going to be plus h minus h. So Iyy, look at this z. So you are in the z direction, so which is minus w plus w. And if you will have it in the x direction, which is minus L plus L, minus L by 2 plus L by 2. If you are going to perform about z direction, then you are going to have x, which is minus L by 2 plus L by 2, y, which is minus h by 2 plus h by 2. Everyone understood this? So what that means is, you are going to perform integration, your limits of integrations are going to be different, which means for a rectangular bar as shown over here, the mass moment of inertia is given as 1 by 12. Note the dimension in z direction is w, so w square plus dimension in y direction is h square n. Then if I want to perform the same thing, it will be 1 by 12. V will be L square plus x square is going to be so z is going to be w square, and x square plus y square, which is L square plus y square is h square. So this is the mass moment of inertia. Everyone understood this? How do we get to 1 by 12? Okay. So 1 by 12. Let's go from here. So you have plus L, 1 by, so this becomes, let me see, did I derive it somewhere here? So let me see. This becomes r cubed by 3, and then basically this dm is the mass that is distributed across the length. So you get 1 over L here. So m by L, and then you have plus L and minus L. That gets basically, and then the L gets cancelled. Let me see if I derive it somewhere over here. Yeah, I haven't derived it over here. Okay. Since you asked, this is dm, so it's going to be L square by 4 minus L square by 4, and this becomes m. This becomes plus. Yeah, it doesn't come 1 by 12, right? Yeah, I don't know. I will check this out and I'll tell you in next class. I don't have that derivation here, but I will explain you that it comes from the integration of em r square. So when you work this integration out, you get it. Again, just take my word for it. In next class, I will derive this. So this is how it is. And what the point here is, this is called as the inertia matrix. Now, please understand, depending upon which point you take, whether you consider a point to be here, whether you consider the point to be here, whether you consider the point to be here, please try to understand this integration changes. One thing I want you to understand is if you are trying to find out the moment of inertia, if we find moment of inertia about centroid, then what happens is, if you look at the moment of inertia matrix, there are actually 9 terms. So you have Ixx, you have Iyy, and you have Izz. You have Ixx, you have Iyy, and you have Izz. And here you have this cross term, which is Ixy, Ixy, then you have Ixz, you have Ixz, you have Iyz, you have Iyz. So if you find out the moment of inertia about the centroid, these non-diagonal terms become 0. So these non-diagonal terms kind of become 0. And only the diagonal terms remain. This is a very important observation, because please try to understand, when you are trying to find out the kinetic energy, we always find out the kinetic energy of the slender rod when the moment of inertia is about the centroid or the centroid of this object. Now with this, what I want to do is, I want to actually work out a problem and kind of give you a flavor for how to solve a problem that has non-zero masses which are distributed across the whole section. So what I want to do is, I want to take an example. Yeah.
So the inertia would be the maximum in the ICC, right?
So inertia would be maximum in the IZZ. That is correct. Now, if you look at this, what is happening is in this particular expression, this distance is h. So your IZZ is actually 1 by 12 m L square plus h square. But since h is very small compared to L, you actually ignore this term and call your mass moment of inertia as 1 by 12 ml square. Does it make sense? Okay. Now the next thing which I want to talk about is how would we solve a very practical problem. So, and I want everyone to pay close attention to this because one of your assignment problems is based on how to solve this type of problem. Imagine that we have a revolute joint. And on this revolute joint, we have this rod. And please understand, this rod is not massless. And here, we have another revolute joint. And this revolute joint is attached to another rod. So this is the revolute joint 1. This is the revolute joint 2. And this is the end effector. Now to solve this problem, first we have to draw the kinematic diagram. So I'm gonna first show V naught, X naught, Y naught. Then I have C1, Y1, X1, and clearly I have V2, Y2, so this is the diagram. Now this distance is, I'm going to call this A1, and this distance is called A2. Now, if you recollect, we have solved this type of problem in the past. Now, what we want to do is, we want to solve the equation, the dynamical equation of motion. So I want to find out the equations that describe the dynamics of this robot. So first and foremost, I will have to solve the forward kinematics. Remember, we talked about forward kinematics, 0h1, 1h2. So I need to find out 0h1 and I need to find out 1h2. Now here I have two links. I have the link with this mass m1 and I have this link with mass m2. Now one thing to observe, that mass m1 of this link is located here. Mass m2 of this link is located over here. And I want to use this information to find out the dynamical equations of motion. This lesson is very important. So what I want you to understand is, first we will solve the forward kinematics. We'll find out 0h1 and 0h2. Now, then what I would do is, I would find out the total kinetic energy. So T is equal to total kinetic energy. There are two masses. So you have the first mass m1 and you have the second mass m2. So what I want to do is, I'm going to do 1/2 m1 Vx1 square plus Vy1 square plus Vz1 square. So which is the translational kinetic energy of mass m1. So this is the translational kinetic energy of m1. Then I would have 1/2 I omega Ixx omega x1 square plus Iyy omega y1 square plus Izz omega e1 square. So 1/2. So now what I want you to understand is this is the first cylinder rod. So Ixx1, Iyy1, Izz1. So this is the kinetic energy of the first mass. Can you see that this mass is distributed? So when the mass is distributed, you have kinetic energy of translation and you will have kinetic energy of rotation. Kinetic energy of translation is mass multiplied by the velocity square. This mass, please understand, is not located at frame 2, but this mass is located at half of the distance at A2. So you would have kinetic energy of translation mx1 square dx1 square, kinetic energy of translation in y direction dy1 square, and last kinetic energy of translation in vz1 square. Everyone understood this? Next thing is, if you look at the kinetic energy of rotation, I want you to understand this is that first link. This link has this fixed, but imagine this has rotational velocity in x, y, z direction. It could have rotation velocity in x direction, and it could have a rotational velocity in y direction. So that's why in general I have written Ixx omega x1 square, Iyy omega y1 square, and Izz1 omega z1 square. Everyone understood this? This is the kinetic energy of rotation. This is rotational kinetic energy. Of n1. Now please understand. Now I have the second mass. The second mass is located at the centroid of link 2, and that is going to be 1/2 m2 vx2 square plus vy2 square plus vz2 square, which is the translational kinetic energy of m2 plus 1/2 I xx2 omega x2 square plus I yy2 omega y2 square plus I zc2 omega v2. This is the kinetic energy of rotation. Yeah.
So for assigning the frame for the for getting the inertia, which direction would be assigned the frame?
Now that's a very good question. Now, So please understand the kinetic energy and potential energy are always defined in inertial frame. Now I want to trace this back a little. Remember, when we performed so, one second. So what I want to show you here is, please understand the kinetic energy or potential energy. These are derived in inertial frame, which means when we are trying to find out 0h1 and 1h2, and when we find out the product of 0h1, 1h2, which is 0h2, everything will be in the inertial coordinate frame, which is in the coordinate frame will be z naught, x naught, and y naught. Everyone understood this? Now, the question that comes in our mind is, when we are trying to find out the inertia matrices, what coordinate system should I choose? So here is the idea. So take this inertial coordinate frame and just place it over the mass m1. So what I'm gonna do is, the inertial coordinate frame, I'm gonna place it over the mass m1, and this inertial coordinate frame is going to be something like this: x0, z0, and y0. Are you with me? Then I'm gonna take this inertial coordinate frame and I'm gonna place this inertial coordinate frame over here. It is going to be z0, x0, and y0. Because what's going to happen is, at the end of the day, how do we get the values of vx1, vy1, and vz1? Those are the position vectors with respect to the inertial coordinate frame. You agree with me? Those are the position vectors with respect to inertial coordinate frame, which means if you look at the distance of this mass, it will be defined with respect to the inertial coordinate frame. So your mass moment of inertia also be defined in terms of inertial coordinate frame. Everyone understood this? So now, as an example, I will show you. Actually, I will derive this in just a minute. I will derive this in just a minute. So please try to understand Vx1 and before actually I start plugging the numbers, I want to make sure everyone understood this. So what we have is, we have a robot arm. This robot arm has two links and two hinges. Those links are not massless. The first link has mass m1, second link has mass m2, first link has length a1, and the second link has length a2. We have to first solve the forward kinematics problem, which means we have to find out 0h1, 1h2, and finally 0h2. All said and done, what we need to do is, we need to find out the position of this mass. This is the centroid. So I would get px1, py1, pz1. Everyone understood this? I will get px1, py1, and pz1. I differentiate that px1, I get gx1. I differentiate that py1, I get vy1. I differentiate pz1, I get vz1. Everyone understood this? So that is the first part. Next part is I'm interested in finding out Ixx 1 omega 1 square, Iyy 1 omega y1 square, Izz1 omega z1 square. Remember, we looked at how to find out the rotational kinetic energy. So remember, we found out omega x, omega y, omega z. So 0 r 0, 0, 0, theta 1 dot plus 0 r 1, 0, 0, theta 2 dot. Are you with me? So we have found out what is the value of omega x, what is the value of omega y, and what is the value of omega z. Are you with me so far? So we have to use this guy. Once we expand, we get something called as the Jacobian. And we use this Jacobian to solve the problem. Now, and I'm gonna write down each and every term, okay? But before I do that, I want to explain for the lead 2. Now, please understand, in lead 2, the centroid is at the distance A2 by 2. You agree with me? The centroid is at distance A2 by 2. So what I want to do is, I want to find out the distance, or I want to solve the forward kinematics problem from the 0th frame to the centroid of the second mass. I want to solve the forward kinematics problem from the 0th frame, the centroid of the second mass. Once I do that, I would get Px2, Py2, and Pz2. Everyone understood this? Let me be absolutely clear. What is the difference here? Please try to understand. And you will have to work this out. Only then you will see. So remember, to find 0h2, we do so 0h1 multiplied by 1h2. Do you agree with me? 0h1, there is no change. But when you multiply by 1h2, what you have is here, please understand, you are gonna have the distances A2 by 2 and A2 by 2. Do you agree with me? Because we are not finding out the distance all the way to the second frame, but since you are trying to find out the distance to the center of the mass, so please understand, mass is not located where the frame 2 is. Mass is located halfway in between frame 1 and frame 2. Everyone understood this? So that's why when you are trying to work this problem out, remember the first column in the third column in the homogeneous transformation will have not A2 but A2 by 2. Everyone understood this? That will be the only change when you solve your forward kinematics problem. And then with that, once you perform this multiplication, you are gonna have a Px2, Py2, Pz2, and then you will take the derivatives and then you will find out the velocity. Everyone understood this? Now let's look at the terms omega x1, omega y1, omega z1. if I want to find out the angular velocity of link 1 in the inertial coordinate frame, I get 0, 0, 0, R0, which is 1, 0, 0. So this is a diagonal matrix. Omega x is equal to 0, omega y is equal to 0, omega z is equal to theta 1 dot. Remember that link only has angular velocity in theta direction. The link does not rotate in x, link does not rotate in y. Are you with me so far? It only has angular velocity in z direction. Now, if I want to find out the angular velocity of rotation of link 2, I need to find out 0 R0 is 1 0. This is a identity matrix, and 0 R1. 0 R1 we already found out. Remember, cosine theta minus sine theta minus cosine theta 0 0 0 0 1. That would be the matrix that's gonna come here, multiplied by the projection matrix. That matrix will be here, and you would get omega x2, omega y2, omega z2. I will repeat this once again. If you ignore this, there's going to be omega x1, omega y1, omega z1. If you take this out, there's going to be omega x2, omega y2, omega z2. Everyone understood this? Take these quantities and put that in this equation, which I have shown you here. And then we have to find out the equation for the potential energy, and equation for potential energy is something like this. So you're gonna have m1 g a1 by 2 plus m1 m2 g, and as you can see, this distance is cosine theta 2, so which is P D2. So basically with that you can find out the potential energy, Lagrangian T minus V, and then what you can do is you can use MATLAB. So now what I want to do is I want to actually work out the problem in MATLAB. So please try to understand this is actually building on the concept that we studied earlier. The most important part is first question.
Professor, when we are calculating the omega, why are we not taking into account the rotation of 1 or 2? So given that there is no theta 3 or theta 2 dash dot, but still
What are you? Okay. The reason is when you have 1, it's 0 R0. When it is 2, it's 0 R1. If you had R theta 3, then it would be 1 R3.
but wouldn't the end vector, the position or the rotation along the first frame to the second frame, or the end vector in this case, will also play the part in the omega?
Yeah, so
Even
theta
it is a mass.
is coming in the picture, 2 not coming in the picture. Theta 1 will come in here, and theta 1 dot will come here. So please understand, our end effector only has 2 theta, theta 1 and theta 2. Theta 2 is dependent on theta 1. There is nothing after theta 2. You agree with me? There is nothing after theta 2. So we have theta 1 that is affecting theta 2. But if we had theta 3 here, theta 2 will come in here. And once again, please understand, this is 0 R1. Okay? This is 0 R0, which is an identity matrix. 0 R1 is the rotation matrix. And if I were to have theta 3 dot, this would be 0 R2. Why is it? Because finally this 0 indicates that is with respect to the 0th frame. 1 indicates, this indicates that is with respect to the, so theta 1 dot. Theta 1 dot is the rotation about which frame you have that rotation. That's why you have zeros. Can you see that? Theta 2 dot. Which frame is this rotation about? 1. That's why you have 0 R. Everyone understood this? This is convoluted. And many a times what happens is first we have to work out the problem and then program it inside MATLAB to solve the problem. But these are the steps. Now what I'm gonna do is I'm gonna take you to MATLAB and I'm gonna explain the code line by line. Everyone understood this? But before I go there, any questions on the formulation? Because I believe there are two problems in your assignment 4 and 5, 3 and 4. I don't know. They are dependent, something like this. There is one more problem that I want to solve, wherein you have a third joint, but the concept is the same. Whenever you are trying to find out the kinetic energy, find out the kinetic energy at the centroid of the mass, nowhere else. Because otherwise, if you don't find the kinetic energy at the centroid of the mass, you will have to take into account the non-diagonal terms, which is Ixy, Ixz, that type of stuff. Here, these are the principal axes of inertia. Okay. Now, what I'm going to do is I'm going to share my screen and I'm going to share MATLAB. Any questions from my online students?
So is that why we are taking the inertia about here, because it's very small compared to the X and Y.
Yeah. So what I want you to do is, if you have downloaded the dynamics, robot dynamics, so this is the R90R robot, and in this R90R robot, what we have is we have G is equal to 9.81, M1 is equal to 0.1, M2 is equal to 0.1. Ignore L1, L2. A1 and A2 are the lengths of the links. Now what I need to do is, first I want to find out the kinetic energy. And what I'm going to do is, I'm going to find out the kinetic energy of translation. I'm going to find out the kinetic energy of rotation. And please understand, the first mass, kinetic energy of translation is 0. I didn't explain that, but let me show you why it is 0. So what you have is, you have this. This mass is located here. Can you see that this distance, no matter what you do, is going to remain fixed? You agree with me? This distance is going to remain fixed, whether it is px1, py1, or pz1. You agree? This point is not going anywhere with respect to this inertial coordinate frame, which means the velocity of this mass vx1, vy1, and vz1 is going to be 0. You agree with me? The next point is, what I want to find out is, I want to find out the moment of inertias. So if you look at this link, understand. So let me write this down here, coordinate frame. This is Z, it's X, y. I'm gonna show it over here. With x, v, y. Now please try to understand. This entire link is fixed. This link is not rotating about this. You agree with me? This link is not rotating about this. This link is only rotating about this. You agree with me? So this link is only rotating about this. Do you agree with me? And if you think about it, since it's a slender rod, we assume this dimension be significantly small and we ignore the kinetic energy of rotation in this axis. Otherwise, it would be like Izz omega z square. You agree with me? Izz omega z square. And Izz will be about this. Right? But since this dimension is very, very small, this value is close to 0. So that's why the kinetic energy of rotation is also 0. So what that means is you have the slender rod which is rotating like this, but this kinetic energy, since this dimension is very small, the kinetic energy of rotation is very small. Everyone understood this? If this rod would have been a big, thick rod, something like this would have been something like this. And then this would have been rotating like this, then there will be some non-zero kinetic energy. But since this is a slender rod, that is very important. It's a slender rod, which means it's a thin rod. Since it's a slender rod, it's a thin rod. That's why the kinetic energy of rotation is 0. Everyone understood this? Okay. The next part is now we go on to link number 2. So link number 2 has the kinetic energy of translation. The kinetic energy of translation is 1/2 m2, and you have this Vx from here to here. And believe you me, we have solved this problem. From here to here, we have this Vx. So this is Vx square. Then we have Vy square. And then we have Vz square. Vx square, Vy square, and then we have Vz, last term is Vz square. So the square term is Vz square. So we have Vx square, Vy square, and Vz square. And then, so we have M2 time Vx square, Vy square, Vz square multiplied by half. And then what I have is, I have this kinetic energy of rotation. Please note, this is 1/12 m square A2 square multiplied by omega x square plus omega y square plus omega z square. So I need to write this down. So I will write this down again. So it's going to be Ixx 2 omega x2 square Iyy Now, please understand, again, what I need to do is, I need to transfer this x, z, and y. Now, understand, this is a slender rod. So, if you have a slender rod, you are going to have Iyy is equal to 1 by 12 m a2 square. I Vz is equal to 1 by 12 m a2 square, and Ixx, just like the argument here, is going to be 0. Are you with me so far? Now here, so Ixx 1 will be 1 by 12 m1 a1 square. Iyy1 will be 1 by 12 m1 a1 square. Izz will be approximately
So we're looking at the Z from the top, right? Yeah, so we look at Z from the top. So there is no A1.
It will take some time. I will have to solve 2 more problems before everything will click. So, and then there will be enlightenment. So please try to work out the problems, because some of these problems, unless you, it's not a spectator sport. No matter how many problems I solve, unless you solve the problems, you will not get hang of it. But and in kinetic energy of rotation, please understand, says Ixx is 0, that term gone away. You have Iyy and Izz. So please note, you have Iyy multiplied by omega yy square and Izz multiplied by omega z square. Okay, everyone understood this? Then you have the kinetic energy of translation plus kinetic energy of rotation. You have potential energy of the mass 1. You have the potential energy of mass 2. And then what you have is you have Lagrangian T1 plus T2 minus V1 plus V2. First kinetic energy, second kinetic energy minus first potential energy, second potential. And then you use a Lagrangian. And then let it run, let it run, let it run. And then somewhere you will get this plot. So basically you have theta 1 dot, theta 2, theta 2 dot. This is the plot at play. So I'm going to show you the code again. And please note that this code is uploaded on Canvas. So you are welcome to actually go through this code and try to solve this problem on your own. Okay, any questions? Omega x, omega y, omega z, and also Vx will come from Px, Py, Pz. That comes from the forward kinematics. The angular velocity will come from the Jacobian Vx, omega x, omega y, omega z. 0 r 0, 0 0 theta 1 dot plus 0 r 1, 0 0 theta 2 dot.
I thought like Jacobian had two parts to it. One is the angular velocity part, and the other one I thought was the translation.
Part, but you don't really need to find the translation because you just need the Vx, Vy, and Vz. You got the equations for Px, you got the equation for Py, you got the equation of Pz. And actually, what I want to do is today, unfortunately, we don't have time. But what I want to do is actually I want to solve the problem from scratch. So basically, let me see. So if you have this robot problem, wherein what you have is you have a revolute joint, a prismatic joint, and a revolute joint. If you have a problem like this, revolute joint and prismatic joint and revolute joint, how would you solve this problem? Again, the way you solve this problem is exactly the same way. You find out the kinetic energy of the first mass, you find the kinetic energy of the second mass, you find the kinetic energy of the third mass, and then basically you go step by step and solve the problem. We don't have time today, but in next class, what I would do is I would actually start from the very beginning and I will work out this problem. The other problem that I really want you to look at is we have this R90R robot we solved. We did RR, RPR, pendulum, and there is a problem with double pendulum, which is RR robot, wherein you have the first link parallel to second link. I would encourage you to look at these problems. But in next class, what I would do is I will work out the problem from scratch, where we will do the forward kinematics. From forward kinematics, we'll find out the forward velocity equations, and we'll use those velocity equations to find out the kinetic energy, potential energy, and we finally solve. So everyone understood the problem that we are going to solve is always we have to solve the problem in pieces. You have to find out the translational kinetic energy. You want to find out the rotational kinetic energy. You have to find out these two kinetic energies for all masses. Then we find out the potential energy. Then use the Lagrangian, substitute that into the equation MATLAB, and then get the answer. Any questions? I don't have time to start the next problem, but what I will do is in the next class, I will solve the problem from scratch. So we will do forward kinematics. We'll find out the Px, Py, Pz, take the derivatives, omega x, omega y, omega z, and then we will find out the potential energy and kinetic energy. With that, I'm gonna stop here. And if you have any questions, I would be happy to answer.